Hello and welcome to our AP Chem discussion on electrolytic cells and our electrochemistry unit. First thing, we've been talking about galvanic cells for the bulk of the unit, and now we're going to look at what happens to a cell when you, instead of allowing it to spontaneously go in a direction it may go on its own, you provide energy and direct it in the opposite direction. Um, when the desired chemical reaction, for example, is non-spontaneous. For example, if you wanted to plate magnesium on from zinc, as opposed to what would naturally happen, um, if you add electrons from an outside source through your wire of a voltage greater than that spontaneous voltage, then your cell will run in reverse. And that basically is everything you're going to see in a cell, and we'll look at this in a graphic in a minute, is going to switch. This converts electrical energy into chemical energy. And some examples, we'll look at in class the electrolysis of water. Let me back up a slide, pardon me. Um, Silver plating, pulling sodium chloride into sodium metal, and other things of that nature. So this is an example of how they plate copper onto an object. You could do this with a penny. You can do this with a key. Naturally, you would expect in most situations that copper being more likely to be reduced, that it's going to be something that's going to be the reduction piece in a cell. But if you provide power in the reverse, connecting the positive lead to your anode you want to be oxidized and the negative lead to your other object in your solution, you could expect a reverse flow, and this is how you would plate an object with copper. Um, if you spend a few minutes on YouTube, you'll find people doing this with all kinds of stuff. This is an example of that first cell we ever looked at, the copper zinc cell, where we saw that when it was allowed to work spontaneously, that it produced a voltage of 1.10. Electrons flowed from the zinc electrode to the copper electrode, plating mass onto here, losing mass from this electrode, zinc ions falling into solution, copper ions being consumed by the solution, and this would be your salt bridge, this porous plate here. Your cations allowed to flow in this direction, anions in this direction, and over time, you would see these molarities change, increase in concentration of zinc here, decrease in concentration of copper here. Okay, that's our typical uh, voltaic cell. If you provide a power source greater than that 1.10 volts and connect it appropriately, your electrons will flow in this direction, plating onto the zinc, pulling mass off the copper, flowing cations in this direction, anions in this direction, reversing the concentration shift that you had experienced. Most importantly, your cathode or your anode is now your cathode, and your cathode is now your anode. And so we can quickly make an assumption that that definition is defined by that electron flow. When electrons are moving away, anox red cat, oxidation takes place at the anode, reduction at the cathode. So these terms changed, and that's okay. Faraday's law says the amount of substance being oxidized or reduced at each electrode during electrolysis is directly proportional to the amount of electricity that passes through the cell. And so, okay, that's Faraday's law. What we're going to do is we're going to apply that into some numerical values. You've seen these on your AP uh, data chart, but we're going to give some definition to a coulomb is an amp second. It's the amount of charge that passes a given point when 1 amp of electrical current flows for 1 second. And that's a value that would usually be given to us in amps. An amp is a flow rate of 1 coulomb per second, 1 amp, okay? And we'll use the symbol I for current, and that's what amperage is. Joules, the amount of energy absorbed or evolved when 1 coulomb of electrical charge moves through a potential difference of 1 volt. So 1 joule is 1 volt coulomb, and 1 Faraday is 1 joule per volt mole. And we'll make sense of all these when we actually apply them here in a few minutes. Conversion factors, and these appear on our AP charts. Amp second is coulomb, 96,500. More specific on the AP chart if you need it. Coulombs is 1 Faraday. 1 Faraday is 1 mole of electrons. The big I current is charge per unit time in coulombs. So we talked about this for amperage. Amperage is coulombs in seconds. Okay. So we use dimensional analysis a lot already in stoichiometry and other places, but dimensional analysis here is huge. We have that skill already on board. What allows us to convert a current, an amperage, multiplied by time to get coulombs, then use Faraday's to get to moles into mass of a reactant, perhaps. Or in reverse, mass of a reactant to moles, to Faraday's, to coulombs, to perhaps an amperage. But it's better if we do it for real. How many grams of chromium can be plated out by passing 2.05 amps through an acidic uh, chromium trioxide solution? This probably should say a chromate solution for 1.0 times 10 to the fourth seconds. So a good amount of time. Chromium must go from an oxidation number of positive 6 to 0. So what you need to notice here is you have a 0, you have positive 6. It's not, it's chromium trioxide. I apologize. Positive 6 here, 0 here. So that's 6 electrons being gained per transaction. So 6 moles of electrons per mole of chromium. So what we're going to do is a little conversion. 10,000 seconds, 10 to the fourth seconds. An amp, again, is coulombs per second. So we can use that to get to coulombs. And keep in mind, Faraday's is 96,000 coulombs per mole. Then we can convert moles of electrons, and this is moles of electrons here in Faraday. Moles of electrons to moles of chromium. And then, since it asked for a mass, what mass of chromium can be plated, convert from by molar mass, moles to grams. And don't call it stoic because there's no chemical reaction. Well, no, it is stoic, but we're not converting between objects within. We're just converting with the number of moles of electrons present. So this is just some basic dimensional analysis, tacking in some new conversion factors that we've never really used before. Coulombs per second in amps, and then Faraday's coulombs per mole of electron. How many hours would it take to produce 25.0 grams of chromium from a solution of chromium trichloride by a current of 2.7 amps? So we're going from chromium trichloride, which is a chromium plus 3, to a chromium 0. So we're going to be reducing, giving electrons to it. In this case, 3 moles of electrons per mole of chromium ion, chromium 3 ion. And so here's the conversion. We have a mass of chromium. We're going to convert to moles. Then for every mole of chromium, 3 moles of electrons being transferred. Then with Faraday's, electrons to coulombs. And then with the amperage, 2.75 amps, which is coulombs per second, we can get to a time unit, seconds. And then we can convert using our common knowledge of time, seconds per hour, and get an hour value for the amount of time it takes to make that conversion. Now I urge you to pause and kind of give these a look. Go back a couple slides and look at those conversion factors and make sense of how these were applied in the last two questions. We went in both directions, from time to mass and from mass to time. So another topic we need to talk about is electrolysis of molten salts. When we electrolyze a molten salt, the cation is always reduced and formed at the cathode, and the anion is oxidized and formed at the anode. The electrolysis of molten sodium chloride takes place in an object called a down cell. Takes a lot of energy, but it's pretty interesting. We have a liquid sodium chloride, so very high temperature molten sodium chloride, producing molten sodium and then chlorine gas. So at the anode, okay, think about what happens at the anode, anox red cat, we have oxidation taking place, all right? And at the cathode, we have reduction taking place. So you take your half cells from your reaction, and you can quickly and easily apply your anode and cathode, because you know that you're taking ions and from them forming your intact element. When electrolysis is carried out in aqueous solutions, there is always the possibility that water will be oxidized and or reduced instead of the solute. In order to predict the products produced when aqueous solutions are electrolyzed, you must determine the potentials of each possibility. So when we consider it happening in water, we must also consider water being oxidized instead of the target ion. For example, so if we electrolyze aqueous sodium bromide, our possible reactions are these. We could be oxidizing bromine. For every 2 bromide ions, we could make 1 bromine gas and 2 electrons. And there's the cell potential for that. This is going to be from either given to you in the question or available on a table. And if this is also on your table, liquid water being oxidized to form oxygen gas, hydrogen ions, and electrons. And there's the cell potential there. In this case, because you have the comparison of the two voltages, the one that is less negative is more spontaneous is the one that's actually going to happen. Okay, so because the bromine reaction is more spontaneous, more less likely to be oxidized, it's going to be the one that happens in our electrolysis cell. So possible cathode reactions, this is the reduction cell. We have sodium ions gaining electrons from sodium solid, or the aqueous water again, instead of being oxidized in the other cell, this is being reduced in this cell, and the voltage there. The second reaction would occur because it is less negative, more spontaneous, and so the overall reaction is, instead of doing plating sodium out, forming solid sodium, we will simply be reducing water. So we will oxidize the bromine, we will reduce the water. Okay? And so our reaction, sodium ends up being a spectator, an ion, because if you look back at what you would have started with, you had sodium bromide aqueous, so it was ions of sodium. Has nothing to do with the reaction, it spectates while this takes place. So we will find and seek out the reactions that will be more likely to take place, and those will be our half reactions. So this method of determining whether water is oxidized or reduced does not always work. In the electrolysis of salt water, brine, we would predict that water would be both oxidized and reduced. In fact, the chloride ions are oxidized instead of water. This is due to some fairly complex factors. We call this overpotential or overvoltage. This is not a feature of the AP test, just a factoid. Here is the the electrolysis of aqueous copper 2 sulfate. At the anode, we would expect water to be oxidized and copper to be reduced. The overall electrolysis of water, these values here. This is a process that we're going to view in class, so stay tuned for that. And that concludes the electrolysis video and the electrochem unit. Please make sure you step back through these slides to make sense of anything that caused you pause. That's what it's here for. So if you have questions, we'll see you in class. Otherwise, make sure you're taking solid notes, and we'll see you soon.